Hey, you got a notification. I went live. So, for those of you who are real cool and decided to follow me on YouTube, I can't blame you. You just got a notification that I went live. From beginning. There we go. Um, okay. Well, hello. Greetings. My name is Mr. Martin, and this is the tests for review by SVGS Physics. So the test is exactly the same as all the others that you've taken this year. You'll have 90 minutes to do it, one full lab block. It'll consist of 15 multiple choice questions. That'll be 2 points each. Rather than doing a lot of these other tests, I did lab-based questions where here are some calculations that have already been made. Here's a missing cell, fill it in, stuff like that. We haven't really done a whole lot of quantitative labs yet. In fact, we've only done 2 so far, and they were both what did you see? So instead, I'm going to have a diagram type question. So it's your guess as to what kind of diagram I'll have you fill out. There aren't that many types. It'll be like electric fields or equipotential lines or both. Cool. And then 5 free response questions, each of those worth 10 points for a grand total of 90 points. So you get 10 for signing your name and all that kind of good stuff. So make sure that you don't cheat when you're filling out your name. Like, hey man, what'd you get for name? I can't answer that one. That's my joke. So let's get into it. Starting with the elementary charge. First and foremost, what is charge? We don't really get it, to be honest. It's just a thing that, and we don't really exactly know why. Just like we don't really exactly know why things have mass. We've been doing research on it, discovering a lot about the Higgs boson and all that kind of fun stuff in recent years. But mass is just a property of matter, and it's that property that causes you to interact with a gravitational field. Charge is just a property of matter as well. But it's a property that causes you to interact with the electric field. And that's it. Protons and electrons have the exact same charge, the same magnitude charge, but opposite signs. So the charge of one single electron is negative 1.6 times 10 to the negative 19 coulombs. We came up with the definition of a coulomb before we discovered a lot about these little particles, so that's why our unit is way, way, way crazy. The charge of a proton is positive 1.6 times 10 to the negative 19 coulombs. But protons are way, way, way bigger. So they've got different masses, but the exact same charge. Meanwhile, neutrons have no charge, so they are neutral. So anytime any object is charged, that only comes from either picking up electrons or losing electrons. And that's it. So if I had an even number of electrons beforehand, and then all of a sudden, Tucker bumps into me and takes 1 billion of my electrons, cool, thanks, man. Then he's negatively charged, and I am positively charged. Because he was neutral before, then added electrons. I was neutral before, then lost electrons. And that's really the only way to become a charged object, is one or the other. The amount of charge that you gain is just related to the amount of electrons that you gain or lose. So you had a bunch of problems in that WebAssign set where it asked how many electrons were transferred, and that's fair game for the test as well. The really small number makes it kind of confusing at first, but it's the exact same thing as, when I help students, I like to say every student in the world, for whatever reason, has 2 candy bars in their pocket. So how many students need to assemble before you have 16 candy bars in the room? It's the exact same thing here. Every electron has negative 1.6 times 10 to the negative 19 coulombs in its pocket. How many electrons need to assemble before you have 2.1 microcoulombs? It's just the numbers are a lot more wacky. But other than that, it's the same concept. Yeah. Few other things about charges. 1, all charges quantize. This means I can have 5 additional electrons or 6 additional electrons or 10 billion additional electrons, but I'm not going to have 5.3 additional electrons. So all of these charge values that I can possibly ever have in my life is an integer multiple of the elementary charge. So 1 times the charge of an electron, 2 times the charge of an electron, 3, 4, and that's it. It's got to be an integer multiple. I'm not getting half an electron charge anywhere. Also, charges are conserved. So this means it's not just going to appear out of nowhere. The total charge in a system has to stay constant unless the system somehow has contact with the outside world. So for example, if I have an object with 5 coulombs of positive charge and another neutral object, no matter what happens, no matter if they touch or not, or one of them gets grounded, or the grounded, never mind, that's introducing it to the system. But if they're isolated, one is positive 5 coulombs, one is nothing, then the grand total of the system is going to stay positive 5 coulombs. And that's it. Even though it might get separated out different ways, you're not just going to gain charge out of nowhere or lose charge. Yeah. If something is grounded, that's introducing electrons from outside the system into it, or vice versa. So in that sense, yeah, the total charge of the system can change. But when I say closed system, that means there is no connection to something like the ground. Yes. At this point, we started learning a bit about the forces. Coulomb's law is F equals K times Q1 times Q2 all over R squared, where Q1 is just the charge of object 1, Q2 is the charge of object 2. You're going to need to convert both of these to coulombs because the value of K there involves coulombs squared. So if they're microcoulombs, nanocoulombs, you got to convert them over first. And R is going to be the distance between the objects. I think that causes a lot of heartache and confusion for people, simply because you think of R as a radius and that's half a diameter, and that freaks people out. But in this case, R is simply just the raw distance from one object to another. Oops. And F is the force each experiences. So a few things about this. Let's say Q1 is like 20 times the value of Q2. Which one's going to feel more force? Or will they be the same? If Q1 is 20 times the charge of Q2 in magnitude, which object will feel more force, 1 or 2? Or will it be the same? It would be the same, yeah. A few hints about that one. Down at the bottom, F is the force that each experiences. Also, if I wanted to find the force that Q1 feels, it would be K times Q1 times Q2 over R squared. If I wanted to find the force that Q2 would experience, force on 2, that'll be K times Q2 times Q1 all over R squared. Q1 times Q2 is Q2 times Q1. It's the same thing. Multiplication is commutative. So yeah, it doesn't matter which one has more of a charge. They both feel the same force from being in the same vicinity together. It's actually exactly like that law that I talked about last semester, where I pull up on the Earth with the exact same gravitational force the Earth pulls down on me. The difference is that I have so much less mass, so I'm going to accelerate more because of that force. But the force value in newtons is the same. It's the same deal between two charged particles. They both exert the exact same force on one another, no matter the magnitudes of their charges. Yeah. And the law, by the way, that I referenced is just Newton's third law, that if I exert a force on you, you exert a force on me with the exact same amount for every single interaction. And that includes electricity and gravity. Yeah. The triboelectric series. First and foremost, you do not have to copy this down. Please don't write it down on your cheat sheet because that would take forever. Plus, this is an incomplete triboelectric series. This is just the chart I found online. Because there are so many materials. There's a lot more that'll fit in there. So yeah, you don't need to know this. I'll give it to you on the test if I'm going to use it, but do know how to use it. So for example, let's say I take some natural rubber and rub it against some, let's go crazy and say polyethylene. Excuse me one moment. I'm going to put this microphone down and cough. Yes. That's so much better. Hey there. Now I'm back. So right, natural rubber and polyethylene. Which one would be positively charged? Yeah, the natural rubber. So odds are the polyethylene would take electrons from the rubber would end up being positively charged. Even though rubber is kind of down on the negative end of this spectrum, polyethylene is more negative. So this is all about the relative positions of the materials together, is how you figure that out. Grounding. Understand, at least on a basic level, what grounding is. The ground is that always essentially neutral-ish region with an infinite reserve of charged particles. So this allows charges to flow freely to or from an object when it's grounded. That means, quite literally, there is a piece of conducting material connecting it to the ground. Think about your houses. If you go outside and look usually around a chimney, if you have one or something like that, you'll see this piece of metal kind of climbing up, and it's the highest point on your house. That's a grounding rod, essentially, and it actually goes into the ground. The idea is that it makes that part of your house a lot more attractive to lightning than the house itself. So the idea is that it's supposed to draw lightning. Lightning is just a discharge like the Van de Graaff generator through some air. So if it strikes that little metal piece, then it'll just travel down that metal and into the ground and away from your house. Versus if it strikes your house, then that's how it burns things. So anyway, interesting little tidbit. So grounding can be used to either charge or discharge an object. Every time I ran that Van de Graaff machine, when I turned it off, I picked up the grounding rod and I touched it in a couple of places just to take that excess charge off of it. But when I also ran the Van de Graaff and held a neutral sphere next to it and grounded the neutral sphere, I tricked some electrons into leaving that neutral sphere, and as a result, it became positively charged. That's a process of induction, which we'll get to in just a second. But yeah, so grounding can either charge or discharge an object. Just requires a conducting rod to be connected down into the ground. And it's also what the third prong is on your plugs. Make sure you know the difference between conductors and insulators. A lot of stuff is actually the same between them. For example, a conductor can be neutral or charged. An insulator can be neutral or charged. Because all it is picking up or losing extra electrons. So think about the balloon. When I rub it on my head, I get the balloon nice and negatively charged simply by adding electrons from my hair onto the balloon. The balloon's an insulator, but it's getting charged. What's different between the two is the method that they can become charged. With insulators, it's pretty much just rubbing. You know, rub your feet across the carpet and touch a door handle. You've been charged up. Versus conductors, it'll be charged using conduction and induction. And in a couple of slides, we'll go over what conduction and induction actually is. Another difference between them is literally just that charged particles are allowed to move freely through conductors, and more specifically, electrons are free to move throughout conductors. And they are not on insulators. Which means once you give an insulator a charge, it stays local to the point where the electrons were built up or taken away. So with that balloon, if you charge up a balloon on your head and then try to stick it to the wall, but you put the opposite side up against the wall, then nothing is going to happen. You've got to take the spot that was actually making contact with your hair and stick that on the wall to make that happen. Conductors, meanwhile, once they get charged, the electrons distribute themselves evenly over the surface. They don't all stay bunched up, because why would they stay bunched up? They hate each other. Instead, they're going to spread out as far as they can, usually across the outer surface of a conductor. But beyond that, there's not a whole lot of difference between conductors and insulators. Both of them can get what's called polarized. If you bring them, and they're neutral, near a charged object, then the electrons are going to flee to one side or the other. What's different is with conductors, the electrons will flee to the far side of the surface of the conductor. That makes the effect a lot stronger. Versus insulators, the electrons are not free to move to the far surface. Instead, they'll just move to the far side of the atom. If it's a negative charge that's nearby, they'll move to the close side of their atoms. If it's a positive charge that's brought nearby. Yeah. So that's that. So that's a little bit of a weaker kind of effect there. Hey, speaking of polarization, there we go. So I've got a picture of a conductor, I've got a picture of an insulator, and you can see that the charges are all lined up the same way on the insulator, but those negatives are not free to move to the far side. Versus the conductor, the negatives can move one way or the other. Remember that through all of this, the positives are not moving. The positive particles are protons. They are stuck in the nucleus of the atom. So it's all about the movement of electrons that make this happen. So when I say, when I have a buildup of positives right here, I don't mean the positives have traveled over to this side of the sphere. Since they make up the nucleus of the atom, which makes up the material itself, that would be horrifying. You would see like an entire chunk of that sphere start to move over to the other side of the sphere, and that would be weird. Basically, things would fall apart anytime they were brought near any charged anything, and life probably wouldn't exist. So instead, the positives just stay put. When I draw a picture like this, I just mean this face has a net positive charge. There are probably still some electrons that are bound to their atoms over there, but I don't draw those because it's a net positive charge. Just like over here, there are positive charges. There are still protons there. It's just that there's an overall negative charge in that spot on the conductor. And that's it. So I mentioned that we're going to get to conduction and induction. The best way for me to remember it is conduction, contact. Conduction, contact. Conduction, contact. Both start with C. And this is where you actually just touch two objects together. So if one is neutral, the other is positive or negative, just touch them together and they'll come away with the exact same charge, both positive or both negative. For those of you at home, that's going to sound real weird. I just realized I could only hear my voice doing that weird thing and didn't see anything else going on. Stuff was falling off my table. Anyway, induction is what I like to call charging by trickery. If you've ever heard induced anything, it's basically you are causing something to happen on its own. So a charged object is brought near an uncharged object, it gets polarized, then the uncharged object is either grounded or separated. Ooh, by separated, I literally mean split in half. If it's polarized and then you split it in half while it's polarized, then cool, the charges are going to stay on the opposite sides. Rather than splitting things in half, the way I did it in class was take two spheres, put them in contact with one another, so that way when they get polarized, the electrons all flee to the far sphere, and when I pull them apart, then the middle one is positive, the far one is negative. But I've got some images that I'll show up here to kind of help you visualize that. In just a second. People are furiously writing, so I'm going to furiously wait for a little bit. Yeah, you can't see it. I'm making a real angry face. while they're finishing up writing down the last couple of things. Fun fact, I just brought a bouncy ball home, and that became the best cat toy that I've ever purchased in my life. I swear. It was like, she is going crazy over that thing, and every day losing it. And I'm not even kidding. It's my only bouncy surfaces are the kitchen and the laundry room, so I'm not messing with it in the kitchen. But every time I walk in the laundry room, she darts in there after me, and then straight up looks up at me and meows at me and asks me to play with her. And I'm like, well, where's your bouncy ball? And then she doesn't help me. Like, it's your job, man. So then I have to search for it. But it's awesome. Her favorite thing is to like hit it with 2 paws and knock it down even harder. And then the ball bounces higher than it was before. And that just like, she flips out about that. It's great. Buy your cat a bouncy ball. And this has a little chunk missing from the side. So sometimes it bounces and goes off sideways in a weird direction. That is the best. All right, so here's conduction. You don't necessarily need to write this diagram down unless you particularly want to, but I'll have this review document, the PowerPoint, as well as this video available for you after the fact as well, if you want to look at that. But contact, it's quite literally just electrons will flow the way that electrons are going to be more comfortable. So they're not going to hop on to the negatively charged particle because they are repelled by negatives. In fact, if they're the negatively charged object and I touch it to a neutral object, the electrons hop on there like that. If my object was initially positively charged when they come in contact, well, now electrons from my neutral object see a positive party going on. They want to be a part of that positive party, and they will hop on board. Ultimately, because charge is conserved, I'm not getting new charge out of nowhere. I'm going to end up with the same total charge between the 2 objects, which means I've got a 0 object and a positive object, so they're going to average out to both positive. What happened to the sphere there? It was neutral. It lost electrons. Now it's positive. That's how you get positively charged. Induction, meanwhile, this is my trickery type thing. I'll bring a charged object near a neutral one. It'll get polarized, and then I'll ground the neutral one, which you can do with a finger if you want to. So if a negative is brought near it, the electrons will flee from my neutral object, and I'll end up with net positive. If the little balloon that I hold near it is positive and I touch it, electrons will come from my hand onto the sphere, and it'll end up being negative. So with conduction, you end up with 2 objects of the same charge. Induction, you end up with an object of an opposite charge. Fancy. Another method of induction that doesn't involve grounding is exactly what I did with the spheres in class. Put them together, they're both neutral, A and B. Bring a charged object near it, and A and B get polarized, but because they're both conductors, the electrons can move back and forth between the 2 different spheres. When you separate it out, then they're both left with a net charge on it. Swanky. All right. And then we talked about electric fields. So electric fields are diagrams that just sort of indicate the force that a charged particle would feel near a charged object. It always points away from negative charges. Sorry, points toward negative charges, points away from positive, simply because physicists decided they wanted to model it after a little positive charge. And that's it. And positives are repelled, negatives and positives are attracted. So every single field line that exists points away from positive, and it points toward negative all the time. Yeah. Not only that, when we say it's the depiction of the force that a test charge would feel, the actual charge of the test charge does not matter. The units are going to be in newtons per coulomb. So it's essentially how many newtons of force I would feel if I put 1 coulomb of charge at that spot in space. Odds are, if I'm going to put anything in that spot in space, it's going to be some value other than 1 coulomb. So let's say there's 20 newtons per coulomb, and I put a 1/2 coulomb charged object there, it would feel 10 newtons of force. That's it. When you're working with electric field lines, I put a positive charge there, it will feel the force directly in line with the electric field. If I put a negative charge in there, it will be 180 degrees in the opposite direction than the electric field is pointing. Simply because we all agreed that electric fields are from positive charges. The way to find the actual strength of an electric field, like we did in class today with points A, B, C, and D, which were great, you've got the electric field equals K times Q over R squared. Don't forget that this, once again, is a vector because it does point away from positives and toward negatives. So Q is the charge of the object creating the field. That's in coulombs. That's not anything to do with the test charge. E is the electric field in newtons per coulomb. And R is how far away from the charge would you like to measure this field strength? And K, just like before, is 9 times 10 to the 9th Newton meter squared per coulomb squared. And I'll give you that constant on the test as well, but you should probably be familiar with it at this point because literally every equation that we're running through uses it. But it's 9 times 10 to the 9th Newton meter squared per coulomb squared. People are still writing furiously, so I'll talk about my cat some more. The second best one is probably, she has this, it has a plastic handle and then a nice flowy fabricy string to it. And it's so long, and yeah, it's wonderful. She loves that thing to the point where if we're not home, I'm pretty sure she carries it around the house and cries with it. Because sometimes when like I'm in bed and she doesn't know where to find me, then I'll just start hearing wow, wow, and her voice, like her mouth is clearly full, and I'll just peek out of the bedroom and I'll see her walk around the corner just dragging this thing after her. We call it her teddy bear now, even though it's not a teddy bear shaped. But I woke up yesterday and found it at the top of the stairs, and it had been downstairs when I went to bed. I woke up today and I found it down the hallway, like almost into the bedroom, which I guess she dropped it when she saw us and came in. Yeah. And then this afternoon, actually, I popped by home real fast and it was back downstairs. So she just carries it around with her and wails when she's lonely. And I think that's adorable. But she also likes to attack it when I'm playing with her. Yeah, like crazy. Exactly. Yeah. But I think that's her second best toy right now. You're going to want to be mildly familiar with some of the more common electric field shapes. Don't go too crazy, but here clearly the positives, the field lines are pointing away from it. The negatives, they're pointing toward it. And at each and every point, it's just the vector addition that you would feel from repulsion and attraction. Repulsion from the positive and attraction toward the negative. When you add the vectors together, you get your brand new direction. So be familiar with these sorts of shapes. If you got 2 negative charges, it looks like this. 2 positive charges, it looks like this. Exact same as the 2 negatives, but the arrows are in the opposite direction. So just hop on and look at this PowerPoint and have those drawn for you. If you've got a capacitor, this is an actual image of electric field lines taking shape. There are straight lines in between the plates, and then they bow outwards, kind of like a dipole on the far outside edges. So when you're sketching field lines, they only start on positive, only end on negative. We've been over that. The number of lines starting or ending on a charge is proportional to the magnitude of the charge. So if I've got one that's 20 times stronger than the other, it really should have 20 more lines associated with it. I'm not actually going to stop and count field lines if you draw a picture for me. Don't worry about that. I'm just telling you so you're prepared when you go out in the world, but I'm not really going to focus too much on that one. Yeah. Field lines are like Ghostbusters with their little, what is it? The old Ghostbusters movie, they've got that, those little laser beam things, and they always yell, "Don't cross the streams," because then it would overpower and explode and all that. It's the same thing for electric field lines. They never cross, frankly, because they can never cross. Imagine that happening. Here's an electric field line, and here's an electric field line. That would be saying, at this point, my net direction of force is this way and this way. And that doesn't make any sense. While you can feel a couple of force vectors in different directions at once, the electric field line shows you the total force direction. And I can't have a total force direction in two different directions at once. Yeah. Yeah. Once again, they're vectors, so the direction in a region can be found by vector addition. Good times. Then we started talking voltage. This, I think, is a little bit easier than electric field simply because it's a scalar, so you don't have to worry about x and y components. You don't have to worry about angles. You don't have to worry about really anything else. Q is the charge of the object creating the voltage. Because it's a scalar, not a vector, make sure that for this Q, you do not ignore the negatives. So Q is the charge of the object creating the voltage, negative included. Negative included. So around a negative charge, I get a negative voltage. Around a positive charge, I get a positive voltage. And if you've got a bunch of charges all in one space, say this is Q1, Q2 is up here, and Q3 is somewhere down here. And let's say I want to find the voltage right here. To do that, I'm just going to have to do V1 plus V2 plus V3. No x and y components, no Pythagorean theorem. It's just find your values and add them up. So that'll simplify down to K times Q1 over R1, the distance from Q1 to this point. R2 is just the distance from Q2 to this point, and R3 is here. So yeah, KQ1 over R1 plus KQ2 over R2 plus KQ3 over R3. Not forgetting that Q3 is negative in the picture that I drew, so this portion of it will be a negative number. Nice. And that's it. I probably should have put something on here about what voltage actually is. Voltage is measured in volts, but it's also the amount of energy per coulomb of charge in a certain region of space. So a volt is equal to 1 joule per 1 coulomb. So if I find that in a region of space, I've got 5 volts, that means that for every coulomb of charge I stick up in that spot, that object will have 5 joules of energy. But if I stick an object with, let's say, 25 coulombs of charge, which is an insane amount. Did I say 25 coulombs? Nice. Times 5, that'll be 125 joules of. Oh, because I said the region had 5 volts. Yeah, sorry. In a region with 5 volts, 25 coulombs. You got it. So that's all it is. Now, equipotential lines are like lines on a topographic map. They don't really have any arrows or directions or anything like that. They're just regions of space that have the exact same voltage. Just like on a topographic map, a line on there is a region on a hillside that has the exact same height. I like to think of positive charges as peaks of hills. I like to think of negative charges as troughs of little sinkholes. So if you scatter positives and negatives around, you get a really funky looking hillside. So you can get funky looking equipotential lines. It's pretty easy around just a single line of charge, or a single charge there, because it's just a series of circles. But once you get others in there, then V1 plus V2 plus V3 plus however many objects causing this voltage has to come out to be the same value at point A and point B. So you can get a weird little shape there. This is what you did the lab on most recently, lab 14. You looked at equipotential lines, and then from that drew some electric field lines. Noting that it's always perpendicular two electric field lines. Always perpendicular. Cool. Cool. In general, we've got a couple of vectors and a couple of scalars that we're dealing with in this unit. The vectors are going to be forces and fields, and those are the only vectors that you're working with in this test coming up here. So with vectors, don't forget that the negative only means direction. Right? So forces, I've said it a bunch in class, but I'm actually going to write it down now. Forces, fields, forget the negative. At first, don't forget it entirely. I'll put a little star here, little footnote, and then I'll say, unless determining the direction, which you need to do every time. But mathematically, do not throw in a negative in front of your Q value. What is happening right now? There we go. Unless determining direction. Okay. And you can determine the direction based on the charges. Positives and positives repel, positives and negatives attract, and an electric field you can treat essentially as if it's positive. For these vectors, your forces and fields, you may have to break stuff into x and y components and take that on. For scalars, this is going to be your energy and voltage. There's no direction, just a value, so you can't ignore negatives and q's. And no need to worry about x and y components, just add them all up, all the individual voltages. Pretty cool, pretty nice. Over Christmas break, my mother-in-law came down and brought these little battery-powered bug-looking type things. I've got little rubber legs and a little tail of a poof ball, and when you turn it on, it starts to vibrate, and it just sort of wiggles its way around the room. That was pretty exciting, too. She liked to punch that thing in the face, then grab it by the tail and pick it up and run with it, just dangling out of her mouth, and sometimes she would shake her head to kill it and throw it against things. It was great. My little violent baby. Oh, no one else is writing. Okay, cool. No more cast stories. Finally, we talked about one thing that I just didn't mention, but I did have up here. This voltage is also known as electric potential and potential difference. All three names are for the exact same thing. It is not the same as electric potential energy. Yep, the only difference is if you see the word energy there, then you're not dealing with voltage. Energy. Oh, the electric potential energy between two objects is K, Q1, Q2 over R. Yeah, just R. Yeah. The force is K, Q1, Q2 over R squared. But the voltage is, and this is going to be in joules, the voltage is going to be in joules per coulomb. So I have one less Q on top. Cool. Voltage and energy are very, very, very close related. In fact, if I know the potential energy between two objects, I can find the voltage there by dividing out one of those charges. That's in joules. Yeah. It's also a scalar. Yeah, but unless you see, like if the word energy is physically not there, I'm not asking about the energy. I'm asking about the voltage. Alrighty. So capacitance. Units of capacitance are coulombs per volt. That's also known as a farad. And that's all that capacitance is. When you take two parallel plates, give them both charges, one will be positively charged, one will be negatively charged, and they'll have the same value charge, but opposite sign. So Q is the magnitude of charge on each plate. You do not have to multiply charge by 2 because there are 2 plates. The Q value is literally just meant to be the charge on one plate. Right there. I'm not going to try to trick you and give you total magnitude coulombs or anything like that. I will just say the charge on a plate is 9 millicoulombs. And that's what you'll use for Q. C is just the ratio between charge and voltage. So if you've got a high capacitance capacitor, it just takes a whole lot of charge to build up a voltage difference between the two of them. If you got a low capacitance capacitor, it doesn't take much buildup of charge at all before you start getting a significant voltage difference. And that's it. Cool. Capacitance again, measured in farads. Yeah. I rub it around, and like this huge ball of like light. It was so yeah. Super bright and like yeah. So like I put like hard. Like, so I put on my bed. I started rubbing around. Is your cat just cool with being pushed over and rubbed around on the bed? That's awesome. That's fantastic. I did the same thing except pulling. I had a fleecy type blanket in the dryer, and I was taking it out, and I'd forgotten to put a dryer sheet in, so it was so staticky. And I was like, wait, hold on. And I asked my wife if she wanted a light show, and we both agreed yes. So we turned off the lights in there and just started pulling blankets apart, and it was like, it was an awesome show. It was great. But doing it with a cat, that makes it even more interesting. Like, if you got a cat, you got light, yeah. Oh man, that's fantastic. All right. The last little bit that you need to know about is the amount of energy stored inside of a capacitor. Yes. The amount of energy stored in a capacitor in joules, just like every other energy is measured in joules. Nice. Keep in mind that this Q is the same as the Q in the other capacitor equation, which was Q equals C delta V. So another way of writing this exact same equation is U equals 1/2. Replace the Q with C delta V. So if all I know is the capacitance and the voltage, I can also figure out the energy in there as C delta V squared. 1/2 C delta V squared. Nice. This is a tool you can always use with multiple equations. Substitute in one variable for some other expression. That's a really, really handy thing to be able to do. Yeah. That's about it in terms of stuff that's going to show up on this mess. Any questions before we move away from this? Hey, yeah. Anything? Okay, let me turn off the stream real fast and then run through it. Yep. Stop broadcast. That didn't work. Okay.